So welcome. Glad to have a full house here. My name is Art Anderson. I'm the Director of Developer Advocacy at Aerospike. If you've never heard of Aerospike before, we are a distributed NoSQL database. And we do all sorts of fun stuff with different data models, graph, p-value, and vector. And so we'll talk a little bit more about vector later on, but this talk is not about Aerospike. It is about understanding vectors, vector databases, getting into some kind of RAG application, working with LLMs, just a lot of these kind of like buzzwords that you've probably been hearing all over the place lately. And so this is kind of like an introductory, getting to know vectors, vector databases, RAG, LLM, all of that fun stuff. And like I said, we'll play around with some code, but this is not like you don't have to be hands-on. I'm going to do some kind of code walkthrough stuff. I'll show you guys some things, but feel free to just kind of sit back, ask questions. We have like 90 minutes together, so we should have plenty of time. So if you have questions, feel free to raise your hand, ask. I like to keep things very conversational, so just if you're wondering about something I'm talking about or we're looking at, feel free to ask. All right. So again, at the top, this first one is just a little website, this QR code here, to create just whatever, random banking stuff. So when we get to the RAG portion of this, we'll be pulling some of those in along with some pre-configured ones that I have and whatnot, and we'll use that in our RAG and get an LLM to answer questions about these things. Down here is the GitHub repo where this code lives. You can run these things either locally. I have everything containerized as well, so if you want to just Docker compose real fast, you can do that. And then it's built to work with an OpenAI API key, or if you have like a Gemini service account, those are the two that I deal with, so it's kind of set up for either or. And then, yeah, you can play around as we go through. So we're going to start talking just a little bit about LLMs, so large language models, and working with them. Then we'll get into vectors and semantic search. So just kind of what is a vector, what is semantic search, and then we'll implement a vector database. So we'll actually build one, right? Like a very, very simple one. But you'll go through the code and we'll actually brute force ourselves some vector search. Then we'll talk a little bit about commercial vector databases. We'll get into specifically the HNSW algorithm. Not like in-depth by any means, but just understanding what it is. That's hierarchical navigable small world, which we'll learn more about as we get there. And then wrap things up with just vector databases in general. Where do we see these in use, and RAG and all that fun stuff. Cool. So LLMs, right, large language models, what is it anyway? So these are basically, it's a type of artificial intelligence. So we use machine learning models and whatnot to create these basically prediction models, right? I feed it a bunch of things called tokens, and then it predicts what the next token is, and these are words generally, right? So we get responses back if we're talking about just like very, very basic language, right? This isn't necessarily limited to just text, right? You can do things with images and music and all sorts of different data, right? And so ChatGPT, Llama, Gemini, these are some of the bigger ones that have been kind of building these things up quite a bit. But basically, it's a AI model you can talk to, right? And we're going to get some kind of interesting responses as we start going along and building out our vector database and integrating with an LLM here. So when you talk to an LLM, you're going to prompt it. You're going to generally ask it a question, and then depending on what you want to get out of it, you might have some kind of additional aspects to your prompt. So if you're just sitting at like the keyboard working with ChatGPT on the web, right, you might just ask a question, do a search, you're looking at like Perplexity or whatever, you're just effectively asking questions. But you might want to put some guardrails around those questions, or you might want to add some additional kind of like instructions to this. Like here, we're asking, do fish breathe air? So in one of these, we ask it, do fish breathe air with the prefix of hey, you're a happy chatbot designed to answer the following question in a whimsical manner. The second time we ask it, we say, you're an angry chatbot designed to answer the following question in a gruff manner, right? And you can actually get different responses. So if we were to actually go out and go to the right screen here, this is ChatGPT that I'm working with right here. If we were to go and ask these questions, so take those 2 prompts, and we actually do that, right? So we say, you're happy, do fish breathe air, so on and so forth. You get this response that's all kind of whimsical and goofy and weird. And then we do the same thing, right? But this time we tell it, hey, you're kind of angry and gruff and so on and so forth. And same exact question, do you fish breathe air? You get this very terse, short, kind of like, no, they get water in their gills and they take the oxygen out of it, so on and so forth, right? And so we can use this to our advantage as we start to interact with these LLMs by kind of processing these prompts or kind of engineering these prompts, right? And so on the back end of things, if you're actually building out like an LLM RAG app, right, you might have some fairly complex types of prompts that you engineer where you're actually asking a question and then you're giving the LLM the answer that you would expect it to give you, and then you're asking another question and saying, based on the response that you had before this, how would you answer this question, and so on and so forth. So there's a lot of different ways that you can kind of work with the prompt engineering here. But this is just a very quick and simple example of what that might look like in kind of influencing the way we get an answer out of an LLM. So, using large language models, this is just some basic code for, this is actually working with Vertex AI, so the Gemini setup here. I actually had this whole thing set up with Gemini, and at the very end, or last minute, I switched over to my OpenAI API key. But there's not really a huge difference here in how we're sending this data over, right? So with Gemini, when we go to start the chat, right, this content, Gemini, all of the Google LLMs actually, they don't really have a concept in their prompts of the LLM itself. It's generally just passing along questions, right? But if you're doing something with OpenAI, you're going to usually send a dictionary, an object over that has the user, the LLM, the user, the LLM, or user computer, whatever, where I'm going to kind of create a conversation. Then I could continue to append to that conversation, because when I'm talking to an LLM, its memory is fully in the context in which I send over, right? So all of the tokens that I get or put together and send over to the LLM, that's basically what it knows on top of its training corpus. So everything that it's been trained on and is able to talk about. So here, right, we're sending over that same do fish breathe air. Now we're not actually doing any real engineering on this one. We're just asking it a question. We get a response, whatever the default way Gemini is designed to give you a response to that. But there's not a lot that you need to do when working with these endpoints. Now, if you wanted to host one of these on your own, there's a little bit more that goes into that, and I will highly recommend at this point. It's generally not worth it. I'll give you a story. I was working on a RAG demo because Aerospike about 6 months ago started kind of launching this new vector search. They were like, we have to have a RAG. Everybody's got a RAG. Let's do this. And so I built out our RAG to work off of all of the Aerospike documentation. And I said, I'm going to host the Gemma open source model. And I went and I got it. I was able to set up a single NVIDIA L4 GPU on a VM in Google Cloud. I had to quantize the Gemma model from 32-bit float down to 16-bit float precision because it was too big to fit in memory. And then, once I had that, and I was able to run it on that one GPU, I could do one user at a time. I could ask one question, get one response, and then if I needed to do another question, I had to wait till that response was done so I could send it over again. That cost me $900 a month. So I switched to using Gemini, and so my buddy Vaibhav over here, he's been doing some work on other stuff with us. I was showing him today that for the entire month of October, he spent 7.5 cents in all of his queries to Gemini. So it's very efficient to use these endpoints, right? Same thing with OpenAI or any of these other ones. Most of the time you can get free credits, right? And not even really spend much at all. All right, so I'm gonna jump the gun on that one. We already took a look and played around with the LLM, but we'll go back and we're gonna look at like changing prompts and adding guardrails as we move along to be able to, again, kind of inform the way that we get responses as we start looking at working with these LLMs, and then kind of slot in what these vectors do for us there as well. Now, improving on this LLM output, right? We've kind of been talking about RAG and fine-tuning. Well, I haven't said anything about fine-tuning it, but I will in a moment. But LLMs generally are stale before they ever even hit the market, right? So these larger models, what was it, like Llama 3, the like 405V model, it's like 32 million GPU hours to train, I believe. I know Meta's got a lot of GPUs, but they definitely don't have 32 million. So it's going to be pretty old data. I think like the larger models, the last I checked, the latest information they had was somewhere around spring of 2023, right? And these are models that were released within the last couple months. So if I want to ask an LLM about something that happened yesterday, I can't, unless I also tell it what happened yesterday, right? So in order to get more kind of like domain specific or relevant information from an LLM, we have to kind of give it that information one way or another. So with the LLM output here, like this is an Aerospike example, how do I create a secondary index in Aerospike, send it over to the LLM, and indexes in Aerospike are created using the secondary index administration tool and so on and so forth. Now, you probably aren't familiar with Aerospike, but that doesn't exist. And this is a real example. So back when I was, again, building this RAG for our brand new vector database, this was a question that I asked. And so asking it without any additional information, it made up a completely hallucinated tool that did all of this stuff. It sounded great, but none of it existed. None of it was in reality. And it wasn't until I then passed along some documentation on how would you create a secondary index, and it was able to summarize that for me and give me an answer that worked and I could use, right? So that's the beauty of a RAG. Now, we also have fine tuning, right? So where would I want to fine tune versus use a RAG and so on and so forth. So fine tuning LLMs. This is like the domain of the data scientist, right? So this is where you're actually going in, right? We've got publicly available data. We have our foundational LLM. So take your Gemini, your ChatGPT 4.0, whatever, right? That's built off of this massive training corpus, and you get this foundational LLM. Then you're going to take some labeled and domain-specific data, and you're going to effectively adjust the weights, right? So you're adjusting the knowledge in which this foundational LLM is built off of. So it could be, adding additional information to the corpus that's specific to what you're doing, what's happening at that time, whatever. And then you're going to then use that fine-tuned LLM as if it was the foundational LLM, and you'll be able to query it, right? So your app hits the LLM and your user is able to see whatever additional data you have. Now, this is going to require quite a bit of work, right? So one, I have to label everything very well. If I don't do that, like my training data is going to be garbage and the results that I get out of that are going to be garbage. And then this takes a lot of resources, right? Like I said, those larger foundational models, they take millions upon millions of GPU hours to train. Like I said, one GPU cost me like $900, and that GPU was like 10 years old at the time or something like that. It was ridiculously outdated. So the time and the energy spent on fine-tuning these models may be a little much for most applications, right? So that's where the RAG comes into play. Now, this looks a little more complex, but in reality, all it's really doing is taking that foundational LLM, and then within your application, you're going and getting your domain-specific data. And generally, you're going to try and get that as relevant as it can be to the question or whatever that your user is asking. And then we're going to pull that back over to the application along with the foundational LLM, right? We do some little bit of prompt engineering, and then you get your answer. So the way that we do all of that, though, generally, right now, is by utilizing vectors in a vector database. So we use embedding models to take data that we want available for people to query. We generate vectors on that, and then we query the database by creating vectors on the questions that people ask. We find the most semantically similar items, and that's how we then send that over to the LLM within our engineered prompt. And that's kind of the crux of what we're going to be talking about today. So, hallucinations, right? It was like what I was talking about when I said asking what a secondary index is. How do we, understand that, or how do we get the LLM to not just make stuff up, right? And that's where a lot of the guardrails and things like that, and a lot of prompt engineering comes into play. So I'm gonna jump over to not this one. There we go, this one. And so this is the server side of the GitHub repo that we have there. So this is basically like the back end that is talking to OpenAI. It's doing all of the handling of our queries, and then this is what's going to be our vector database as well. Now, I have really just like one endpoint that we're going to be using here. And this is this like REST v1 chat, whatever. But you'll see there's a bunch of commented out stuff inside of this. So all of these things commented out right now, we're just literally taking whatever you type into that box and we're passing it over to the LLM, right? So that's how we got the like, what do fish, or how do fish breathe, or do they breathe air, or whatever. And we pass that off and we get our answers. Now, I'm going to start by trying to add some kind of guardrail here. And so what this is, you'll see this is called prompt hallucination, because this does elicit hallucination. But effectively what we're trying to do here is just add some additional information to what we are sending over to the LLM. Yeah?
Could you just increase the text size a little bit?
Oh, sure. See if I can remember what the... How's that?
Yeah.
All right. So this here called prompt hallucination. Now, let's see what this prompt actually looks like. If I can get that to open up. So in here on our LLM, we have this, you're a helpful assistant answering questions about creatures of mythology bank, right? So that's that weird bank that we're going to be talking about. It's a fantasy bank that services only creatures of mythology. It offers a range of banking services from savings accounts to credit cards, applying to almost all mythological creatures. Here's the question. Okay, so, and this is string, and we formatted it, and we're just going to put this question in there. So if we go back to our main file here, and we've got this prompt hallucination, and then again, question equals text, right? So we're going to pass through whatever we put in here. So I'm just going to go ahead and save that. And this is a fast API unicorn application. So this is over here. This is set to reload. So anytime you change something and save it, server just starts over. We don't have to restart it. Okay, so I'm going to ask a question. I'm going to say what products. If I can type. Do you offer? All right. And so this is going to create a response for us. And now you'll notice that this is a lot of information about the products that are offered here at this mythical bank. So it tells us, hey, yeah, over here, Creatures of Mythology Bank, we offer a wide range of products. Here's some savings accounts, some checking accounts, some credit cards, some loans, some investment services, right? These LLMs, I mean, they're pretty imaginative because it literally made all of this up. None of this is real. I mean, none of this is real, but none of this is especially not real, right? Completely made it up. But if you were to turn that prompt off and just say, what products do you offer? It's just like, I don't know, I'm OpenAI. We're like a LLM company, right? So like, we've done enough to kind of give it a task, but it's still not very good at that task, right? We need to actually give it some information or guardrails so that it will at least not hallucinate these things. So if we go back over here and let's get rid of this. So we'll just comment that back out. And then we're gonna say, we'll use this one here with no hallucination, right? So let's see what that looks like. Down here, right, it says your helpful assistant, blah, 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 same thing. But we've now added a little bit more context, right? So it says the bank was founded in this thing by this guy and so on and so forth. Using only this information, answer the question. And if you're unable to answer the question, just let us know, right? You need more info or something like that. So if we were to go back over here, and we'll ask the exact same question, right? What products do you offer? And hopefully, we'll get a different response. So a lot less information, right? It basically says, hey, we offer a range of banking services from savings accounts to credit cards. However, I can't give you any real specific information about what we offer because I don't know, right? So you'll need to pass more along so that I can help you out here. So if we were to go back again, right, we can prompt with our vector search, which we'll do in a little bit, but this will pass along even more information, right? So we're gonna now attach our guardrails, and then we're going to have context, right? So additional information that will pass along. Basically what you're doing is you're telling the LLM like, hey, here's the answer. Now tell me what it is, right? I'm gonna give you a bunch of information and I want then you to summarize this for me. But how do we give it information, right? And that's again where this vector search, semantic search vectors themselves come in. Now I will preface this, it's pretty wild. So like I said, started off building this RAG application, I don't know, maybe 6 months ago. And 6 months ago, I started with Llama 2 70B, right? That had a 4K context window. So what's a context window? It is effectively how many tokens I can give to the LLM for it to then generate a response, and then all of those tokens that it generates as a response for me, right? So the total of those two, how many tokens I give it and how many it gives me, is, or has to be within that context window, right? So a token itself is generally about 3/4 of a word, right? So you can just like, on average, think of it like that. So 4K, not a lot, right? You take a couple documents and you create tokens from those, pass that along into the LLM, right? Very quickly, you will run up against that 4K limit. So about 3 or 4 weeks in, I switched over to Gemma, the open source model, because that had an 8K context window. So double the amount of data that I was able to send over to that, right? Gemini 1.5 Flash, I believe, is 1 million token context window. If you go to the Pro model, I believe that's 1.5 million. The ChatGPT 4.0, depending on what plan you're on, I think goes up to 1 million or 2 million context tokens. So the window size in which we can send this data over, this context over, has massively grown just within like the last 6 months, right? So a lot of folks think like, oh, well, why do I need a vector database when I could just send it my entire documentation with every question, right? Because that takes time, right? They have to process all those tokens. Why send it a bunch of stuff it doesn't need to process? But also I think just, this opens up a lot more windows as far as like having a conversation around like a RAG, right? So being able to carry along that context and carry a conversation, because again, my interaction with an LLM is only going to go as far as the data that I send to it every time I ask it a question, right? So if I'm having a conversation, I have to append my new question and the new response to that conversation. And that whole conversation has to fit in that context window. So this just opens the door to longer, more fruitful conversations with LLMs, and hopefully more data as we pass that through. All right, so let's talk vectors and semantic search. What is it? What are we doing here? But first, any questions before we jump forward? Sweet. All right, so vectors. These capture the semantic meaning of source data. So like I said earlier, like we're gonna talk text here, but I think like right before this, there was somebody doing a RAG demo kind of talk on video, right? So text, video, images, music, right? Any kind of like unstructured data or really just data, right? We can pass this through, it's called an embedding model. So these are just different models. Some of them are going to be like specific to an LLM, some might be like a CNN if I'm doing kind of like an image recognition thing, but what they're doing is they're generating a vector, a list of floating point numbers, right? And so we are going to take these vectors and we're going to store them in a database, and then we're going to query them. And we'll kind of see a little bit later kind of how we're going to do that. But again, the whole kind of main function here is we're going to take some data, we're going to put it into an embedding model, we're going to get this list of floating point numbers, right? Yeah?
If, for example, you're using like OpenAI's LLM, do you have to use their embedding model, or is there?
No, absolutely not. So if you guys didn't hear the question, if I'm using OpenAI's LLM, right? Say I got ChatGPT 4.0, do I have to use the OpenAI embedding model to create the embeddings for my vectors? Absolutely not. The one place that is incredibly important is the vectors, or the model, excuse me, that I use to generate my vectors on my source data must also be the model that I use to generate vectors on my queries. Otherwise, right, you're not gonna be able to match those things up. But otherwise, no, you don't have to, you're not stuck. We're gonna be using, it's like a AL mini LM6 or something like that. I can't remember exactly which one. But a very simple, small text embedding from the Hugging Face sentence transformers, right? It doesn't matter though what LLM I'm using. It's all about being able to grab that and then, or create those and then query them later on. Cool. So here's a very simple example. Now, we're going to, in this very first part, we're going to be creating vectors of 2 dimensions, right? So very, very simple. But as we kind of move on and start getting into our little bank example, we're going to be creating vectors with 384 dimensions. The RAG that I use has vectors, so I was using Nomic AI's embedding model, 768 dimensions, but then switched to Gemini's embedding model because again, it's fast and it's cheap. And that's also 768 dimensions. So the model that you use to create your embeddings is going to really be dependent on what it is that you're trying to get out of it, right? So there's definitely what appears to be a point of diminishing returns as far as like the number of dimensions within your vectors. So is 768 half as good as 15 whatever? No, not generally. 384 for what we're going to do later on is going to work pretty well for us as well. So Again, it's going to really be dependent on what your need is and what your use is. But like I said, for this, we're just going to talk in 2 dimensions, okay? And so for this example, we are looking for a house. We want a 2,500 square foot house with 6,500 square feet of land. I think this is kind of fun. We're in like Manhattan talking about giant houses on giant land. I live in San Francisco, which is also a place that I would never be able to afford that. But anyway, that's what we're looking for. So there's 9 houses on this list. And so we have land area and we have floor area. And we've kind of plotted those and given like the kind of optimal there in the middle, what we're looking for. Now, to embed these, we're going to basically like generate this 2-dimensional vector by normalizing the land area and the floor area by dividing by the largest value within each column, right? So here, the example, we've got house 1, right? Land area of 8,800 square feet. We've got the largest land area of 11,780, right? So we're going to divide 8,800 by 11,780 and we get 0.7470. Now, we are about twice as worried about the floor area versus the land area. So we are going to divide the land area by 2. So effectively giving it a weight of half as much as our floor. And so what we'll end up with here for each of these houses, a single vector, 2 dimensions. 1 dimension is the land and 1 dimension is the floor, right? Now, for the search, we have our ideal house, right? So we said 6,500 land, 2,500 square feet for the floor. So we're going to generate a vector for that as well, right? So this is going to be our like source vector, our query. So we're going to take that and we're going to get that 0.2579 and 0.6417, right? And then we're going to figure out how we want to search this. So 2 very common ways that you'll see with vector search is either cosine similarity or Euclidean distance, right? Now there's other methods out there, Hamming, Manhattan, and so on and so forth, that a lot of these vector databases support. But these are the 2 that we're going to talk about. These are probably the more common ones that you'll see. So cosine similarity, we're going to range from like -1 to 1. Bigger numbers are closer. Euclidean distance, smaller numbers are closer. And so we're just, again, looking at like basically the angle between 2 vectors or the distance between 2 vectors. So Euclidean distance. For our example here, using the Euclidean distance, we see that A is the closest to our target, C is the furthest from our target, right? So we've just plotted these points here. And then here's the actual code, right? So like for our little brute force database, if we wanted to do our Euclidean distance, this is what you're doing there. So it's just and we're using the squared Euclidean, so it's just x1 minus x2 squared plus y1 minus y2 squared. It's not too complex, right? So I've noticed that Euclidean distance works pretty well for low dimensional vector spaces. I don't know. Somebody else decided to put this good for text spaces. I like the cosine similarity more for text spaces. But again, it's going to depend on what your application is and which one's going to be best for the data. So you might have to try them both. Cosine similarity here, we can see that C is actually the closest target, and then E is about the furthest away because, again, C is pretty much on like the exact same trajectory there as our sources. And again, there's the code. This is what we're using for our cosine similarity. Again, not too complex. Now, of these, right, if we were to look at the actual results, So here, A and C, I love how we switched from numbers to letters. But if we look at these results here, right, cosine similarity and our squared Euclidean, number 6 is our best case with the cosine similarity. Number 9 here is our best case with the squared Euclidean. If you actually look at the values, right, this is land area of 3575 and a floor area of 1270. This is 6650 and 2825, right? I think if, you know, again, we're in a pretty low dimensional vector space here, so it's not hard to just look at the numbers and see which one is probably the best. But when you look at it this way, right, I would say that's probably our better option there, right? So the squared Euclidean works well. Yeah?
Also, a stupid question. You mentioned like high dimension vector space and low dimension. Maybe it's basic, but if you can explain.
Yeah, so like high dimension vectors would just be longer lists, right? So like a vector is effectively just a list of floating point numbers, right? And so here, our vectors have a dimension of 2, right? So that's a fairly low dimension, 2 floating point numbers within this. As we, again, get further on, higher dimensional vectors, we're gonna be working in 384 dimensions with our text embeddings later on. And so it's really just how many numbers exist within that list of floats. Yeah.
Doesn't the model that you choose decide the
It
number
does.
of vectors? Okay.
It does. So the question was, doesn't the model you choose decide the number of vectors? And for the most part, it does. But there are some out there. So like I mentioned briefly, Nomic AI was the first like kind of larger dimension vector embedding model that I was using that actually applies it's like the Matrushka representation learning or something like that, but think like Russian nesting dolls. And so you could actually slice and dice your vectors. So even though it defaults to 768 dimensions, I could go to like 512, all the way down to like 64 if I wanted to. So it's not always going to be exactly that they determine that, but they will determine at least like the range in which you'll be able to work with. Yeah, cool.
Thank you.
Yeah. All right, so like we just saw over on the last slide, best results, squared Euclidean. Now, if we actually plot these things out, right, looks pretty good. And we can see like, yeah, cosine makes sense, right? Some of these other ones are also not too far off, but that one was our best result. So we kind of talked about some of these notes as we went, right? So 2 dimensions, very low. That said though, in the world of like vectors and semantic search, you might do like binary vectors, you might do super high dimension, you know, some of these create, you know, a couple thousand dimensions and things like that. Again, it's going to be very dependent on what it is that your application needs. We could have added other dimensions, right? So price, that's kind of a big one I might want to consider when I'm looking to buy something. Number of bedrooms, how old the house is, where the house is, you know, any of those things, those factors that go into purchasing that home. So we could have extended that out. Yeah.
Do you have any suggestions on assessing the quality of the embedding for your domain?
That's a great question. If anybody didn't hear that, how do you assess the quality of the embeddings for your domain? Generally, it's like through testing, sentiment analysis, things like that, where like, these are the results I got. How good are they compared to what I would expect to get when I do this, right? So you can think of it where I used to, so before I got into the world of databases, I actually worked for a machine vision company. And so I worked with convolutional neural networks for like image recognition. And I had lots of customers that were very, very surprised when they were creating these models. So you could think of it as like we had this like kind of black box model that you then fine-tuned with your images and your stuff. And they would be blown away at how much labeling was required to add to this. But then what would blow them away even more was the fact that when they were done, the only way that they could determine if what they had done worked well was to go through with another set of data that they knew exactly what should be the answer, and then test and see if they got the right answers. And so it's very similar with this, right? So if I'm creating embeddings and like not going anywhere near or getting anywhere near the results that I would expect, then I'm probably gonna wanna change something, whether it be the model, whether it be the way that I'm doing the embedding. So, if I'm passing along metadata or not, or any of those other kind of factors that go into like the data that we're collecting and storing within these vectors. Cool. So we, like I said, real vectors, hundreds of thousands of dimensions, potentially. Each vector in the search has the same number of dimensions. So with a vector database, right, you're going to generate an index. You're going to create your vector index in which you're going to be doing this search on, and the dimensions that you use, I can't have one have 5 and the other have 3, right? If all my houses are going to be determined by land area, square footage of the floor, and then price, bedrooms, age, neighborhood quality, every one of them has to have something for each of those dimensions, right? It needs to be the same to be able to get good results on that search. Real models, weights determined by AI models, CNNs, things like that. And then, again, this one we talked about already. When you create the vectors on the data, you need to use the same model to create the vectors on the search. All right, questions on that before we move forward? Yeah.
That last slide, it said normalization wasn't a requirement. Are there any advantages to normalizing the data before?
I don't think so. I don't know. I mean, I think it really depends. Like for this one, we were the embedding model with our very basic normalization. So it's really going to be dependent on the model. The data that you're going to be putting into the model, you might have to do some kind of like broad formatting or whatever, that kind of stuff. But generally, the model itself is going to take care of that part for you. Cool. All right. Any other questions? All right. So let's talk about setting up our little database here. So like I said, we're going to be using this all mini LM L6 V2 blah 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 sentence transformer. Basically, what this does is it takes some text and it creates 384 dimension vector. Like I said, that's the code right there. That's all it takes. Very simple. And you can get that off Hugging Face. All right, so our RAG application flow. We already talked about this when we were looking at this before, right? We've got a user, they're gonna put in a query. We've got our sentence transformer here, generate embedding. We're gonna go do a vector search. We're then going to create kind of this like prompt with the additional context, right? An engineered prompt. And then we're gonna pass that over to the LLM, which is then gonna stream this response back to the user. So again, we're gonna kind of go through all of this. What's really important here though is that first step, we need a database of vectors to search, right? We need data to be able to pull over to the actual application. So let's go take a look at some more code. All right. So if we were to head over to our, well, let's look at the embedder first. So like I said, this is pretty straightforward here for the actual embedding model itself. So we're using, like I said, sentence transformers, that library, and then we are just defining the model, just like that. And then we are going to use this create embedding function that literally just returns model.code and the data, right? So we're gonna pass in the data as like our bank information, like the different products and things that we're gonna be looking at. We're going to then also use this, like I said, to generate embeddings on the query, so whatever questions we happen to ask. so that we can search that data and then get that back. Now, here we have our squared Euclidean and our cosine similarity. And then this is just to create a little vector if you want to see it. But so we are going to use cosine similarity for this one. So this actually gets kind of set over here when you run that main application. We're defining cosine similarity, and then also kind of how we're defining the result of that similarity, right? So we want like basically larger similarity is better. So like if we switch to the Euclidean distance, we would want smaller, right? Because it's the distance now that we're looking at. So this is just kind of setting this on the initialization here. So that is our embedder, which really these guys aren't doing anything for the embedding themselves. It's just how we're going to compare them. This is all that we're doing on that front. And that's just logging this, not really being used. Here's our database. So there's a number of products that we have in this kind of like data loader and brought over from a CSV file, excuse me, that is in the GitHub repo that you'll be able to see there. And so we're pulling out those products and we're adding those to the database. Now this is all in memory, right? Like we're not actually storing this in an actual database, just in memory as we have this running. This is that set comparator. So again, just saying, hey, we're going to be using this cosine similarity. We want to see the larger as the better result. This is just how we add entries to this, right? So if I want to add an entry to the database, I need a way to be able to create that vector, then set that data in. This is getting all those entries. And then here's our similarity search, where we are just brute forcing this, right? So it's literally, I have my vector, and then I'm just going to search one by one and see what's the similarity between these two. Next one, what's the similarity? And as I get these, I'm gonna append to this array of like the top 5 basically, or this list. Sorry, I've been doing a lot of JavaScript work lately. So we're gonna just keep appending to this list until we get to the top 5, right? As we've gone through this and we have like the top 5 results. And that's how we'll return these back to our front end, right? So it's that simple. Now we'll talk about some of the pitfalls of that in a moment, but it's really, truly just comparing, right? I have 2 items, let's get a comparison, and then let's pull all of those together. Now, if we go back over to our main function, or actually here, let's go back to our LLM function. We briefly looked at this prompt with vector search, right? So the big kind of extra piece here is that context part, right? And so what we're doing is we're telling it the same thing we said earlier, right? So this is pretty much the same prompt as the like prompt without hallucination, but it's added this tiny bit of context, and it says here is the data that you're going to have available to you to answer questions that you might be asking here. Now, if we go out to our front end, if I can remember where it's at, there we go. If we come out here, you'll notice on the sidebar, there's this kind of like little viewer, right? So we can see all the different products. There's 20 products in here by default. So when we initialize this, right, we get these like 20 products, and then we're able to start kind of messing around with these. And so we can ask it a question now, right? Before I forget though. We're just gonna uncomment this, right? So this is that extra bit. So just to go through this real fast, we have our text coming in. So the first thing that we do is we create an embedding, right? So this is going back to that embedding model that we have. So we're gonna create the vector, We're starting this time thing, that's just to see how long it takes, right? Results is gonna be the similarity search with the embedding, and then 5, right? So what does that mean? Well, if we go back to our little database, this is just like the part of that API, right? That says, here's the embedding, right, the vector, and I wanna get the top 5 results for this particular vector. That's it. And so we're passing that along, and that then knows which one of these vectors, or what vector to use to start brute forcing to figure out what the best distance, or not distance, excuse me, angle between these are. And then here it's just gonna go through, and it just tells you which ones it used, and then we get that actual prompt to stream back to the user, right? And again, now you can see in this format, we're passing along not just the text, but also the context, right? So again, giving it more information. So let's save this. And let's head back over here. And now we're going to ask it the same question: what products do you offer? And we've brute forced 5 of the ones that best represent that. Now, it's probably not the best question to be able to get like a great result from these, right? But we can see now it says, hey, we have some savings accounts, we have some checking accounts, we have some mortgages. And so like Kraken Seaside Savings, we can actually go look. Do we have a savings product called Kraken Seaside Savings? We do, right? And here's information about it. It's a long-term investment that's safe as long as you don't disturb the deep sea, right? And it's telling us all of that information because we've now given it that data to then have an informed response to answer our question. These are products that we actually offer, right? This is real. And so if we wanted to go out here, let me go to the right side. Oh, there we go. And we wanted to take a look at our forms. Wow, we have 33 submissions. That's great. Yeah, hopefully nobody put any like swears or anything in here. But yeah, so we could go ahead and we can download as a CSV. And we'll open this guy up here. Maybe. There we go. I did not want to use Excel. That's fine. But what we'll do is we'll head back over here. And in our data loader, we have this get default products and then this like append products. And so this is actually going in and grabbing our file. So we'll actually be able to load some of this additional data here. And let me go out to the GitHub repo. Oh, okay. I forgot that VS Code doesn't make it easy to switch directories. Let's do this. upload this guy over here. That hopefully works. All right, and so now we'll try and load some products. There we go, we have 53 products now. Cool, right? So if we were to take a look, we've got checking products. Oh, that's a real interesting one. Cake, cool. You guys got real, real creative. Is this a new one? I don't know. I can't remember. But anyway, we have 53 different products here. What's one that somebody created? Like, just shout it out if you created it cool.
Save silver.
Save silver.
Wealth management.
Oh, wealth management. Okay, cool. So, save silver. So, are you a werewolf tired of being burned by your wealth? Let's save silver. I love this. This is great, right? So let's ask a question about that. Do you have any werewolf safe plans? Oh, check it out. Save silver. Oh, and there's a werewolf wealth management one as well, right? But we just added that, right? We created a vector, we asked it a question, and then we were able to semantically find that that happened to be, if you notice, that's the top result. And then we have our werewolf wealth management after that, and then we get into vampires, three little pigs, and some other stuff, because we probably need to set some sort of threshold, right? Which you could go in and play around with if you wanted to. But yeah, right? That's it, right? That's the whole thing right there. We took our stuff, we generated a vector, we then put it all in a little database, we search based off of those same vector embeddings, and then we can pass that along to an LLM until we get relevant results to the domain that we're working with, right? All right, question?
So it returned 5 at the top, right? Because you had it set to 5.
Correct.
Then it only went into detail at 2. Is that because you set a threshold for some kind of similarity?
No. So if I had set a threshold for similarity, we could have probably reduced the number of results that we got at the top there. The rest of that is just 100% ChatGPT saying like, you asked about werewolves, so I'm only going to tell you about werewolves. So, yeah, awesome. Yeah.
Are all those real that it found? I guess the vector matches are definitely real.
Yes, exactly. Yeah. So save silver. We know that actually exists, and then werewolf wealth management we can also come in here and see is real, right? So we're reducing hallucination by passing real information. Yeah.
How can you tell it, like, I'm not looking, because I'm a werewolf, I'm looking to protect against werewolves, basically.
Oh, like I don't want other werewolves to steal my
like,
stuff.
Werewolf safe means like, okay, save me because I'm a werewolf, and that matches, but there's the other version of it where it's like, I want to protect myself against werewolves,
Sure.
or my money against werewolves.
Yeah,
basically.
so there's gonna be, there's definitely some fuzziness to all of this, right? So when you're creating vector embeddings, when you're generating these vectors, the model itself is going to really play into like how that stuff is handled, right? There are ways to, some of these might, just like in natural language processing, might do some stuff where like it's, tokenizing and lemmatizing and kind of creating this like semantic picture of what you have in there. And it might treat the word safe differently when it's in proximity to other words and things like that, right? So like I have a safe versus I want to be safe, right? Like I don't want to be a safe, I want to be safe, right? So like the models themselves are going to kind of play into that. So you might find some are better than others at being able to identify that stuff.
Thank you.
Cool. Yeah.
I guess, well, it's amazing what RAG can do. At what point it's more effective to use RAG compared to actually training the model or doing LoRa or something like that? Or
Yeah, so like fine tuning is gonna come into play when this is not enough, right, basically. That's how I look at it. Now, like I said earlier, right, RAG is kind of the domain of the developer and fine tuning is like the domain of the data scientist. There's going to be a lot of situations, I would say the majority of situations that at least I deal with, where RAG is absolutely going to be much easier to implement, faster, stay relevant longer, all of that kind of stuff. But when you have very, very specific tasks that require lots of processing, things like that, that's where like your fine-tuning stuff is going to come into play. So again, I know it's kind of like a cop-out answer, but it's always going to depend, right? Whatever your application is, it's going to be variable. Oh, yeah.
If I want to make it as a chat, so I want to hook to and I also like progress information from my previous conversation with it. Should I first do a search in vector database and then put all the information?
So that's a really great question, and that's actually where like these kind of like agentic workflows come into play very nicely. So I could effectively like ask a question, and I could then have something look at the question and say, is this asking about what it's already asked about, or is this asking about something that I need more context from, right? And then I can, depending on what path I'm going down, I can then go to my vector database and get more context and then pass that along, or I can just pass along the conversation that we're having to the LLM to then get a response back to that. And then I might even throw like another kind of set of rules on the other side that say, now I want you to tell me, is the answer that you've gotten, is that semantically correct for the question that was asked, right? So like if you put these guardrails up and you ask, you say like, hey, you know, I'm a bank and blah, 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 and I want to do this. And then you ask it like, how do I boil an egg, right? I would hope that it doesn't tell me how to boil an egg because it's only supposed to be answering questions about our mythological bank. So that's where like, again, you can kind of go in there and set up some of the those extra pieces to check, is this doing the thing that it should be doing? Which kind of goes back to like the sentiment analysis and other things. Are we getting the results that we would expect to be getting from this? Cool. All right. Yeah.
A little bit of an off, not technical question, but how much of your all's customers would you say, you know, employ RAG, and then are they satisfied with it, or are they seeking more fine tuning typically?
Well, so our customers are not really there yet.
Okay.
We're still like we're available as a vector database,
Okay.
but we're not like fully GA yet. So
Okay.
it's a lot of preview stuff.
Okay.
I would say the majority of the use cases that I have seen are RAG based one way or another. Now I do have, so like I have a demo that I built that is, so combining kind of like key value, graph, and vector. And the whole vector piece of that has nothing to do with RAG, and it's everything about image recognition and semantic search across images. So basically being able to type in like, it's a retail demo, so I want blue Nike shoes, and then it shows me all the retail items that are blue Nike shoes, right? So that's one place that like, kind of leaving the RAG sphere. But yeah, RAG is kind of like the big one, and now everybody's trying to go down the graph RAG route, where it's like, cool, now that I've got my kind of semantic search, now I'm gonna pass it a whole graph, a knowledge graph, right? Yeah, so it's, it evolves like every day.
Thank you.
Yeah. Cool. Any other questions? Yeah.
Just with the RAG, like in an application, you might have, stuff that you need to generate the answer, but that you don't want someone to know, like, is that an issue?
Yes.
That's a whole nother topic.
So that's a whole other topic. So, but I will say, like, generally, if the RAG, the data that you're using for the RAG is going to be in any way producing an answer for somebody to look at, all of that data better be available to whoever is able to see that answer. There are, like, obviously there's like business accounts that you can set up, or hosting your own LLM, which, like I said, is ridiculously expensive, but where they won't at least use your data for training on the models, so it doesn't become like part of the public knowledge. But yeah, anything that goes into the RAG better be available for the person seeing the response from that, or else, yeah. Cool. All right, so let's talk commercial vector databases. So what are some of the drawbacks of our database that we just created here? Well, 2 vectors. If we were working in the 384 dimensions there, right? It's like 1,000 operations, just to compare 2 of them, right? And so we had 53 in there. We brute forced every single one of those to get the top 5, right? So if you were to start to expand, right? You get up to 1 billion vectors. That's a lot of brute forcing. That doesn't really scale very well, right? Also, 384 vectors, 3 kilobytes of data, or excuse me, 384 floating point numbers within a vector. It's about 3 kilobytes of data. Again, trillion ops per comparison if you're at 1 billion vectors, and you're looking at like 1.3 terabytes of data. So that grows massively. So this is where you might want to turn to a commercial database. Now, this is the API that we have in our little setup. And you're going to find that it's really not that different from like a commercial vector database. So here we're just telling it how we're doing our search, right? So we're telling it, hey, I want to do cosine similarity, and we want the larger response to be the better option. We're going to add entries to our database, right? So I have to be able to put vectors in, and then I'm going to need to be able to search across those vectors, right? Those are kind of like the core components, right? What is the index that I'm working off of? How do I add data? How do I get data back up? Now, commercial vector databases, these are going to do things like pre-compute your vector index. So they'll utilize nearest neighbor algorithms or approximate nearest neighbor algorithms. Lots less in computational requirements. Still lots and lots of lookups, but the way that they do these are generally going to be like in-memory caching, and then like we'll talk about in a moment here, utilizing a graph effectively, but many graphs to be able to pull these things together. So this here is another GitHub repo. This is just a RAG demo that I built, right? So the one I was talking about earlier. And this works with the Aerospike vector database. So if you want to play around with it, you can. But just out on GitHub, you can see that code. And again, commercial API, define the index, add the entry, how do I search, right? So not much different from what we created ourselves, but this is going to be able to do a lot more for us than our little brute force setup. Yeah?
I know this is a complicated topic, but could you explain briefly, in layman's terms, what it means to index vector database?
So yeah, so it's basically, right, when you think about like just a database in general, right, I have an index. I might have like a primary index, and then I might have like various secondary indexes, but it's really just a way to like do a common search across a set of data, right? And so with a vector database, my index is going to be effectively like, how am I going to search? What is the parameter for searching across all of this data that I have in here? And so I might create a vector index that says like, cool, I'm going to be searching on cosine similarity, right? And so then my database is going to go and it's going to generate an index. So like, as we'll talk about in a moment here, Aerospike uses HNSW, right? And so that's creating this hierarchical series of graphs that is identifying, like within each vector, what are its approximate nearest neighbors, and so on and so forth. And it's basically creating an efficient way for me to search across that data. So if that helps to answer that question at all?
So, but when you're doing when you're trying to compare an input vector to something that's in the database,
Mhm.
you don't know what the input vector is in advance, right? So I'm not understanding when you're pre-calculating these.
Right, but I know that I'm searching on cosine similarity.
Yeah.
So I can group things together based on what they're like similar from one to the other, right?
Okay.
So I know, like, as I'm traversing this like series of graphs, as I get lower and lower, based on how I'm comparing my current vector to the actual index of vectors, I know, okay, this is now, I'm in the neighborhood of everybody that should be close to this,
So
right?
you're comparing the vectors that are already in the database to each other and
Right.
grouping them.
Exactly.
And then you're labeling.
I mean,
them
that is just
I know that's a
very simplistic look at it, yeah, but for the most part, yeah, it's just, again, identifying that like efficient search across all of my data. Like what's gonna be the easiest and fastest way for me to identify this. All right, so, like I said, HNSW, hierarchical navigable small worlds. This is a pretty complex topic, but we'll kind of just do a high level overview here. And so what we're doing is we're starting at a high level. Think of it as like, I have 2 entry points in a big graph, right? And so depending on how my current search vector compares to those 2 entry points, I'm gonna choose one of the two, right? And so then, I'm gonna drop down a level. That graph is gonna be slightly more complex, and I'm going to then figure out where I best fit on that graph. And then once I find my best fit, I'm gonna drop down to the next level. And that's going to be even more complex. And I'm going to find my best fit, and then I might drop down to another level, and so on and so forth, right? So a good example of this is like I said earlier, I live in San Francisco, right? And yesterday I had to fly here from San Francisco right to New York. And so how did I get from there to here, right? Well, I navigated a bunch of small worlds. And if you kind of go from the middle out, right? I had one flight that took me from SFO to JFK, right? So that's my top kind of layer, right? And then within that, on one end, I had a bunch of little things that I did. So I took a lift to the airport or maybe a train or whatever. When I got here, I took a couple different trains and then I walked a little bit, right? And so it's each of those kind of levels on how I'm getting there, right? The closer you get to either end, the more detailed you're looking at the overall picture, right?
So going back to the earlier concept
Yeah.
of indexing, so these indexes allow you to start at a higher level, and then you can drill down from there.
Correct, yeah. And this is, and so again, this is like one example of a variety of these like approximate nearest neighbor algorithms. This is kind of like the very common graph flavor that you see with this, but there are many different ways, and a lot of the vector databases utilize or may utilize different types of these kind of search algorithms. This is the one that Aerospike is kind of focused on, but it's not the like be all end all of identifying vectors in a database. So back to our little floor example, right? Or a land versus floor example. Say we had a whole bunch of houses. Again, this is just that kind of zooming in, right? So we know like this area here is good-ish, right? So we stop looking at everything outside of that and we just focus on that area. And then once we're in that area, we can then kind of brute force against those handful to get, if you really want, like the nearest neighbor within that area. And we can then see, okay, this is a good result for what it is that we're looking at or looking to get out there. So that's another example of that HNSW. Now, what's interesting about Aerospike I promise this isn't like a sales pitch or anything like that. It is actually kind of neat. So we do ridiculously fast key value retrieval. Right? That's our whole like bread and butter. Right? We have all these like patented algorithms on how we access solid state drives that basically give you like RAM-like performance and all this stuff, super cheap as far as hardware is concerned. I don't do sales, so I don't know how much the software costs, but probably not cheap. But we have a free version too, so. But anyway, so we do this like really super fast key value store, and we do it in a way that allows you to distribute data across massive geos, individual clusters, all sorts of cool things. And so when we started to get into the vector space, we're like, well, wouldn't it be cool too if you could like just distribute your HNSW across a bunch of nodes within a cluster, right? And so that's what we built. And actually we have a patent on this brand new way of distributing HNSWs across the nodes within a cluster, right? So if you want to scale an HNSW, you run into these challenges. One, if I wanted to do this at scale in like a locking mechanism, right? So I'm serializing writes. All of my writes need to like lock the HNSW to then add this to the index, update everything, and then I can do the next one, right? Because if I don't have that lock on there and I'm parallelizing writes, then I'm gonna run into index corruption, right? Most likely. Because I'm updating the index and I'm updating the index and maybe the index gets updated because this changed, but then this other thing changed, and now because all of these things are happening at once, you can run into issues with that. So this is gonna be slow, not great for scale, and that's going to potentially introduce a bunch of issues, errors, corruption. So what we do is we actually have a series of these smaller HNSWs that each of them themselves take on writes, and then an overall HNSW that effectively like takes all of those together, so merges together at a time frame, and then heals itself and does all sorts of other cool stuff. So just kind of an interesting way. Like I said, this is like a brand new way of doing this kind of scalable HNSW setup. Cool. All right. So, yeah.
So, like, you give some of the advantages of using Aerospike, and I think some of that comes back to like Aerospike's like being a fast key value store, and like there's that general trend of moving towards like, oh yeah, use PG vector or something, so like a dedicated database. So like maybe flip that around. Like, are there any advantages of using something which is like more built from scratch as a dedicated vector database rather than like just leveraging it? A company that already has a lot of experience in building databases and key value stores.
So honestly, like something like Aerospike, the like tacked on kind of nature of the HNSW piece, the vector store, whatever, works really, really well in like multimodal applications, right? So let's say that like I want to, well actually I talked about this earlier, right? I created this retail website that combines key value vector and a graph, right? And so I have 3 different data models. I've got key value stuff that I'm gonna use to be able to look up just individual products, right? I wanna go to a product page, I wanna see that. I then want to be like doing recommendations based on what that product looks like, so I'm doing a vector search on images, and then potentially vector search when I'm doing just searching across my data set. And then I have a graph that's like all my customer data that's then like aggregating all of that information. So specifically like who bought this item, what are the top 10 items that they bought, and then across all of those people that bought this item, like how do I aggregate all these things, right? So it's like 3 very different things. All 3 of those things exist in a single database, right? And so that's where this really comes into play, is like, I'm not doing a 100% vector only kind of setup. I need other things. I need to be able to store right alongside my vector, maybe some other key value data, that I want to pull out there. Maybe I am doing something with the graph, whatever. I'm growing beyond this stuff. I'm not looking to do it fully in memory because we also do all of that on, we can do all of that on disk, right? So same performance that you would get, like, let's say like Pinecone in memory, we can do that right there on a solid state drive, right? But if I'm doing something that's like specifically vector, all I care about is vector, then I'm probably gonna go to something like a Pinecone or BB8 or whatever. And those are gonna actually have, you know, libraries that have embeddings built right into them and like embedding models and things like that. So that's where you're gonna see a bigger kind of like the pros of going to those. Whereas like with an Aerospike or a PG vector even, or something that's like kind of tacked on to another database, you have that additional, you know, building ground to build out more of an application. Cool. All right. 10-minute warning here. So I actually only have like 2 slides left. That's perfect. So where do we see this stuff used? Similarity search, right? Fraud detection, enhanced search capabilities. We actually, I'll be talking about this tomorrow if anybody's interested in the morning. We just launched Aerospike Search. So it's like the search on our website was just total garbage. It sucked. You search stuff, it didn't give you anything worthwhile. So my buddy Bob back there and Tori, she's not here right now, but she'll be here tomorrow. The 3 of us got together and we built out a new search engine. So it uses Aerospike key value plus the vector. So we're doing like an inverted index keyword search plus vector, tie them all together with some cool stuff, right? And so this just builds on that, right? We're able to build this like keyword thing, and then vector takes care of all of the weird fuzzy stuff, right? So it picks up on like, oh, I misspelled the word, or you know, something where I don't have to build that into other search functionality. Vector just kind of takes care of it for me. Transaction categorization, risk assessment, predictive analytics, and then RAG, right? So chatbots, you know, using these for regulatory compliance, risk management, sentiment analysis, loan and mortgage processing, all sorts of fun stuff. So that is all I have. We do have, I think, some time for questions, but I just want to throw this out here as well. Feel free to join our Discord community, and then that right there is like a free trial for the Aerospike Vector. It spins you up a little sandbox environment that you can play around with, build out an application. Give it a try. Like I said, we're not fully GA yet, so what we're really looking for is people to try it and tell us what they think. And you know, did you enjoy it? Did you run into issues with it? That kind of stuff. So we'd love to have you guys give that a go as well. But that is it. So if you have questions, feel free to ask. I'll be hanging around. Otherwise, thank you very much for coming.